For centuries, Jupiter has been one of the most recognizable objects in the night sky, a massive, swirling giant that seems almost familiar at first glance. Early astronomers pointed their telescopes toward it over 300 years ago and immediately noticed something strange: a gigantic storm carved into its surface. That storm, now known as Great Red Spot, has been raging ever since, growing, shrinking, and shifting in ways scientists still struggle to explain. It's not just a storm, it's a system so large it could swallow Earth whole, spinning endlessly in a chaotic atmosphere filled with violent winds and towering clouds. But the deeper scientists looked, the stranger it became. Jupiter isn't just a planet with storms, it is a world made of storms. Its entire surface is a constantly shifting mosaic of bands, swirls, and turbulent systems crashing into each other at incredible speeds. Bright zones and dark belts stretch across the planet, driven by winds that can exceed hundreds of miles per hour, creating a dynamic, ever-changing landscape that never truly settles. Unlike Earth, there's no solid ground beneath these clouds, just layer after layer of gas, pressure, and unknown depths that extend thousands of miles downward. For a long time, scientists believed they had a decent grasp on how this giant worked. The upper atmosphere had been studied, its basic chemical ingredients identified, and its weather patterns tracked over decades. It gave the illusion that Jupiter was, in some sense, understood. But that confidence came with a massive blind spot. Everything we thought we knew was based only on what we could see from above or measure from a distance. And that leaves one enormous question unanswered. What's actually happening deep beneath those clouds? Because the truth is, no one has ever directly seen what lies below. And what's hidden there may be far more complex and far more important than anyone expected. But the deeper scientists tried to look, the more Jupiter seemed to push back. Those iconic clouds aren't just beautiful, they're a nearly impenetrable barrier, stretching thousands of miles downward and growing thicker, darker, and more extreme with depth. Unlike Earth's atmosphere, which gradually thins out, Jupiter's only becomes more intense, with crushing pressure and rising temperatures turning the environment into something almost impossible to study directly. What appears calm from afar is actually a chaotic, layered system where visibility drops to zero, and the rules of physics start to behave in unfamiliar ways. At one point, scientists attempted to break through that barrier. In 1995, Galileo spacecraft released a probe straight into Jupiter's atmosphere, hoping to finally uncover what was hiding beneath the clouds. For a brief moment, it worked. The probe transmitted valuable data as it descended, revealing hints about temperature, pressure, and chemical composition. But then, without warning, the signal vanished. The extreme conditions, intense heat, crushing pressure, and violent turbulence overwhelmed the probe, cutting it off completely. It was a stark reminder that Jupiter doesn't easily give up its secrets. Since then, missions like Juno mission have taken a safer approach, orbiting high above the planet and scanning it with advanced instruments. These observations have helped map the upper layers of the atmosphere, detecting compounds like ammonia, methane, and traces of water. But even with this technology, scientists are still only scratching the surface. Everything beyond those upper layers remains hidden, inferred only through indirect measurements and educated guesses. That's what makes Jupiter so frustrating and so fascinating. We can see its storms, track its winds, and analyze its outer chemistry, but the deeper layers remain almost completely unknown. It's like trying to understand an entire ocean by only studying its surface waves. And for years, that limitation left scientists stuck, forced to debate theories without ever being able to confirm what was really happening below. So if direct exploration wasn't enough, the only option left was to rebuild Jupiter from scratch, inside a computer. So instead of trying to physically reach Jupiter's depths, scientists turned to something far more powerful: simulation. If they couldn't go into the planet, they would bring the planet into their computers. That's where a new study, led by researchers at the University of Chicago and Jet Propulsion Laboratory, took a completely different approach. Rather than relying on partial data or simplified assumptions, they built one of the most detailed models of Jupiter's atmosphere ever created, designed to recreate what's happening far beneath the clouds. What makes this model different is how much it tries to capture at once. Jupiter's atmosphere isn't just a mix of gases, it's a constantly evolving system, where extreme heat deep below meets cooler layers above, forcing molecules to rise, sink, break apart, and recombine in thousands of different chemical reactions. At the same time, massive currents of gas move vertically and horizontally, dragging these molecules through wildly different conditions. Previous models usually focused on one side of this, either the chemistry or the physical motion, but never both in full detail. This time, scientists combined them. They merged complex chemical reactions with hydrodynamic simulations, allowing them to track not just what molecules exist, but how they move, interact, and transform over time. It's the first time these two systems have been fully linked in a model like this, creating a far more realistic picture of how Jupiter actually behaves beneath its surface. And because of that, the results weren't just more precise, they were unexpected. What the model revealed didn't just refine our understanding of Jupiter, it challenged it. And this is where things start to get controversial. For decades, scientists have been locked in a quiet but intense debate over one simple question. How much oxygen does Jupiter actually contain? It might sound like a small detail, but in planetary science, this number changes everything. Oxygen on Jupiter is mostly tied up in water, meaning the amount of oxygen tells us how much water exists deep within the planet. And that, in turn, holds clues about how and where Jupiter originally formed. The problem is, past studies haven't agreed. Some models suggested Jupiter contains only a fraction of the oxygen found in the Sun, far less than expected. Others argued for much higher amounts, but the data was never clear enough to settle the argument. Depending on which study you looked at, Jupiter's origin story could shift completely. Did it form in its current position, or did it begin much farther out in the solar system before migrating inward? The answers seem to change depending on who you asked. Now, this new model is adding fuel to that debate. According to the latest analysis, Jupiter likely contains about 1.5 times more oxygen than the Sun. It's a significant jump from some previous estimates, and not everyone is convinced. Models, after all, are only as good as the assumptions behind them. While this new approach is more advanced, it's still a simulation, not a direct measurement, and that leaves room for doubt. There's already been quiet discussion in the scientific community, with some researchers questioning whether the slower atmospheric mixing seen in the model could be influencing the results. Others suggest that earlier measurements may have missed key factors entirely. Nothing is fully settled yet, but one thing is clear: this debate is far from over. And the reason it matters so much goes far beyond Jupiter itself. Because this isn't just about numbers, it's about the origin story of an entire solar system. The amount of oxygen inside Jupiter is directly tied to how much water it contains, and that detail holds a massive clue about where and how the planet first formed. In the early days of the solar system, temperature played a critical role. Closer to the Sun, water existed mostly as vapor, making it harder for planets to gather and hold on to it. But farther out, beyond a certain boundary known as the frost line, water froze into ice, making it much easier for growing planets to accumulate mass quickly. So if Jupiter really does contain more oxygen than the Sun, as this new model suggests, it points to a very different formation scenario. It implies that large amounts of icy material may have been involved in building the planet, hinting that Jupiter could have formed much farther away from the Sun than where it sits today. Over time, it may have migrated inward, reshaping the structure of the solar system as it moved. That idea alone has huge implications, not just for Jupiter, but for every planet, including Earth. And it doesn't stop there. Understanding how Jupiter formed helps scientists refine the models they use to study planets beyond our solar system. When astronomers look at distant star systems and spot massive gas giants, they rely on what we've learned from Jupiter to interpret what they're seeing. If our understanding of Jupiter changes, it could mean we've been misreading those distant worlds all along. In other words, this single detail, how much oxygen exists deep within Jupiter, could ripple outward, changing how we understand planet formation across the entire universe. But even that might not be the most surprising part of this discovery. But just as scientists were starting to process what this meant for Jupiter's origins, the model revealed something even more unexpected. Its atmosphere may be behaving in a way no one saw coming. For years, researchers assumed that the gases inside Jupiter mixed rapidly, with material constantly cycling between deep layers and the upper atmosphere in a matter of hours. That idea shaped nearly every previous model, influencing how scientists interpreted everything from chemical composition to temperature changes. But this new simulation tells a completely different story. Instead of a fast, constantly churning system, Jupiter's atmosphere may actually be moving much more slowly, up to 35 to 40 times slower than earlier estimates. That's not a small adjustment, it's a massive shift. According to the model, it could take weeks for a single molecule to travel through just one layer of the atmosphere, rather than just hours, as previously believed. That changes everything. A slower mixing process means the chemical signals scientists detect in the upper atmosphere might not represent what's happening deeper down. In other words, the data we've been relying on for decades could be telling only part of the story, while the rest remains hidden far below, evolving at a pace we never accounted for. Naturally, not everyone is ready to accept this right away. Some researchers argue that more observational evidence is needed before rewriting the rules of how Jupiter works. Others suggest this could explain why past measurements have been so inconsistent. Either way, it raises a bigger question that scientists can't ignore. If something as fundamental as atmospheric mixing has been misunderstood for this long, what else have we been getting wrong? And that question opens the door to an even bigger realization. Despite everything we've learned, Jupiter is still largely a mystery. For all the data collected by missions like Juno mission and decades of observations from Earth, scientists are still piecing together a puzzle with massive gaps missing. The deeper layers of Jupiter remain completely out of reach, hidden beneath crushing and extreme temperatures that no current spacecraft can survive for long. What we have instead are models, more advanced than ever, but still built on assumptions that could change with the next discovery. There's also the possibility that Jupiter isn't just complex, it might be fundamentally different from what we expect a planet to be. Some researchers have quietly suggested that processes deep inside the planet could be behaving in ways we don't fully understand yet, especially under conditions that can't be replicated on Earth. There's even speculation that unknown interactions between chemistry and physics at those depths could be skewing the data we collect from above. These ideas are still unproven, but they highlight just how much uncertainty remains. Future missions may bring us closer to answers, but they also risk uncovering even more questions. As technology improves, scientists hope to probe deeper, refine their models, and test these new theories against real data. But if this latest research has shown anything, it's that every time we think we're getting close to understanding Jupiter, the planet reveals another layer of complexity. Which leads to a final, unsettling thought. If one of the most studied planets in our solar system can still surprise us like this, what does that say about the countless worlds we've barely even begun to explore? In the end, Jupiter isn't becoming clearer. It's becoming more mysterious. What once seemed like a well-understood giant is now revealing cracks in everything scientists thought they knew. From the debate over its oxygen levels to the discovery that its atmosphere may move far slower than expected, each new finding raises more questions than it answers. The deeper we try to understand Jupiter, the more it challenges the very models we rely on to explain not just this planet, but the formation of entire solar systems. And that's what makes this discovery so powerful. It's not just about one planet, it's about the limits of our knowledge. If we can misinterpret something as massive and as close as Jupiter, then what are we missing when we look at distant worlds orbiting other stars? Every assumption we make, every model we build, could be overlooking details that completely change the story. So the next time you see images of Jupiter's swirling clouds, remember, what you're looking at is only the surface of a mystery that runs far deeper than we ever imagined. And right now, we're only just beginning to realize how much we still don't understand.